Alright, in chapter 5.2 we're going to be looking at how to evaluate and graph polynomial functions. The first thing I want to do is just go through and there's a table on page 337 that we want to look at, and it's talking about the common different types of polynomials and how you will see them. And there's a few different things you need to know. You need to know degree, which is going to be the highest exponent of that polynomial. You're going to want to know the type of polynomial that it is, what it looks like when it's in standard form, and then I'll show you an example of what it might look like. Okay. So something that has a degree of 0. This is what's known as just a constant. An example of this would be f of x equals a to the sub 0, which is just a number. Okay, does not have a variable, so we know that an example of this would be something like this: y equals 4. Okay, that's just a constant value. It's a horizontal line. There's no changes in direction. It's just a constant line. And we know that also, if you were to throw this in here, I'm going to put it in yellow so you know that it's not always there. Really, this is x to the 0 power, because x to the 0 power is 1. That's why the degree is 0, because that's the highest exponent of the variable. Alright, the next type is degree 1. This is a linear function. And a linear function is in the form that looks like this: some value, some coefficient, x, and then plus, I'll say that's a sub 1 actually, and then plus some value, a sub 0. Okay, and you can tell here that the highest degree of the exponent is 1. So an example of this might look like this: y equals 4x plus 3. Okay, that would be your a sub 1, that would be your a sub 0, and then x with a degree of 1. The next type of degree is a degree 2, which is a quadratic. Okay, we've already looked at quadratic functions back in the previous chapter. This is going to look like this: f of x equals, I'll start with a sub 2 this time, x to the second, plus a sub 1, x to the first, plus a sub 0. And an example of this might look like this: 2x squared plus 4x minus 2. Degree 3 is called a cubic. Again, we're just kind of working our way through the list here. I think we go to degree 4. Is f of x equals a sub 3 x to the third plus a sub 2 x squared plus a sub 1 x plus a sub 0. An example of this could be something as basic as y equals x to the third, and then they could add anything they want to it. They don't have to have every single term. It could be x to the third minus 2. It could be missing the two middle ones here, but as long as it has a highest degree of 3, which it does, then it's a cubic function. Degree 4 is called a quartic. And this looks like this. It's the last one we're doing here: a sub 4 x to the fourth plus a sub 3 x to the third plus a sub 2 x squared plus a sub 1 x plus a sub 0. And again, same thing here. As long as it has the highest degree of 4, it doesn't have to have all the other values in between. It could just be y equals x to the fourth minus 3x squared plus x. This particular example was missing the third power and the constant value, but still the highest exponent is 4. Okay, so example 1 wants us to kind of use this table of values to tell whether or not the function is a polynomial. And if it is a polynomial, they want us to write it in standard form and to tell a degree, type, and the leading coefficient. Okay. So the first example, example 1a, says h of x It's got x to the fourth minus 1/4 x squared plus 3. So the first question that we need to answer is this a polynomial? And to tell that, you need to first look at the exponents. Well, all the exponents are positive integers. Okay? There's no square roots in the exponents. There's nothing like that to mess it up. So this one is a polynomial. So first, then you look to see, is it in standard form? Well, in this case it is. It goes from highest exponent of 4, the next highest is 2, and then no exponents. This one is already in standard form. So the only other things that we need to answer in this problem is, what's the degree? Well, the degree is 4. The highest exponent is 4. The type, since the degree is 4, we look at our chart, we know that degree 4 is quartic. And the leading coefficient, I'll abbreviate here, is the number of the coefficient that is in front of the term with the highest exponent, which in this case is this term here, and the coefficient of that term is 1. And these are all important when we start looking at in the behaviors of graph. Now we'll start looking at, what's it doing as x goes to infinity, or what is x doing, what is the graph doing as x goes to negative infinity. So these few things are going to kind of help us out a little bit. Part B, I'm going to go through these a little bit quicker here because some of them we won't have to do all this work for. Part B, it says g of x, and again, h of x, g of x is all just y, really. It's just trying to distinguish the difference between the two. 7x minus square root of 3 plus pi x squared. And this one tries to confuse it because it throws in these square roots, it throws in the pi. But if you look at the variables x and x squared, there's nothing there like a negative exponent. There's no fractions where the variable's on the denominator, so this is a polynomial. So let's put this polynomial in standard form, which means highest exponent, which in this case is the x squared. So I want to put it first. Pi x squared, sorry. And the next highest term is the one to just the first power, which is 7x. And then the constant term, which in this case is the square root of 3, it always goes last. So this is in standard form. The degree of this problem, the highest exponent is 2, which means the type is quadratic. And the leading coefficient, I'll abbreviate even more here, is pi. Alright, part C. F of x equals 5x squared plus 3x to the negative 1 minus x. Right off the bat, you should be noticing this negative exponent, which means that this is not a polynomial. And I'm going to, in yellow here, just circle why it's not. Okay, you cannot have negative values in the exponent. That will give you a fraction with a variable on the denominator. All right, and part D, k of x equals x plus 2 to the x power minus 0.6 x to the 5th. This one is also not a polynomial because it does not have an integer as an exponent. It's got a variable as an exponent. And we'll get into that into a later chapter where you have x as the exponent. Okay? So that's example 1, just showing you the different types. Example 2 and 3 deal with evaluating. The first one's going to be something that you've done before, and it's going to be pretty easy. The second one will be something new, but it's also pretty easy, and it will help you later on with later chapters. Example 2 says, take the function f of x, 2x to the 4th minus 5x third minus 4x plus 8. And it says evaluate that expression when x is equal to 3. And this is called direct substitution. Okay, Okay, this is stuff we've done before, and it's not hard. It's just, at times a little time consuming, but all we're going to do is just plug in 3 into all the x values, and I like to rewrite the expression with parentheses wherever my x values were. That way I know exactly where I am plugging that 3 in. And it's nice to have parentheses too, because sometimes when you have negatives, people tend to forget to put the parentheses. Okay, I know exactly where those 3's are going. Okay, and then from there, you would want to use your calculator. 2 and then 3 to the 4th power. It's going to get me 162. I'm just doing one term at a time here so I don't mess up. Minus, and then 5, 3 to the 3rd power, which is 135. And then minus 4 times 3, which we know is 12. Shouldn't need a calculator for that. And then plus 8. So type all that in. 162 minus 135 minus 12 plus 8. It's going to get you 23. Okay, that's what's called direct substitution. Okay, it's something we've done before, but a little time consuming, and it's hard to do if you don't have a calculator. Okay, the next one is called synthetic substitution, and pretty easy. A few steps to it, but we're going to do the same example. So I'm going to kind of scroll down here so you can see the example we just did, and we're going to use the same example, but we're going to do it synthetically, and we should get the same answer of 23. So here's how you set it up. You've got this little L-looking shape, and what you're going to do is you're going to put whatever it is you're evaluating with over here on the outside. I'm evaluating when x is equal to 3. And then what you're going to do is you're going to start, hopefully this is in standard form, which it is, 4, 3, the 2 value where the exponent is missing, and then x to the first, and then no x. This is already in standard form, so what I'm going to do is I'm going to write out each coefficient right here. So starting with my highest exponent, x to the 4th, my coefficient is 2. Moving on to the 3rd power, my coefficient is negative 5. My x squared term is missing, so my coefficient is 0. And that's something that people tend to forget. My x term, my coefficient is negative 4, and then my constant term is 8. So 2, just make sure I'm not forgetting anything, 2, negative 5, missing term is a 0, negative 4, then the 8. Okay? So from here, the steps are pretty simple. Always bring down your first term. And then there's a pattern, okay? 3 times 2 is 6. So 3 times 2 is 6. It goes here. Then you add negative 5 plus 6 is 1. You do the same thing. 3 times 1 is 3. 0 plus 3 is 3. It's that same pattern all the way till you get to the end. 3 times 3 is 9. Negative 4 plus 9 is 5. 3 times 5 is 15. 8 plus 15 is 23. And look what we got. The same thing we've got in the previous problem. And we're going to do some synthetic division, which you will use this process a lot more often. Okay? Alright, the next thing we'll look at is going to be on page 339. I'm just going to put the book up underneath here because I don't want it to draw all this out. On page 339, give me a second here. In your textbook, you will have this little chart. It has a key concept. Okay, we're going to be looking at end behaviors of graph. Is it starting from negative infinity, taking a turn like it is right here, going down and then curving up. And these are going to help us get an idea what our graph looks like. Okay, if we know the degree is odd and the leading coefficient is positive, we know the graph is going to look similar to this, where it starts from coming down below and finishes it going up to the top. Okay, if our degree is odd, but this time our leading coefficient is negative, then it's going to be coming from the top area and then finishing out going down to negative infinity. And we need to get used to some of these terms here. If you look at it, let's look at just the first square here. If the degree is odd, which means that the degree is 5, 3, or 1, we know that it's going to be a degree odd. So leading coefficient, we look at it. If the leading coefficient is a positive value, then here's what we need to look at. F of x and x. These are the two things we're going to be looking at. And if you kind of follow your graph, and you start here at the origin, and you follow your graph as x goes to negative infinity. So I'm going to start here. I don't want to write in my book here. You start here, and you follow it as x gets smaller and smaller. It's not going to curve anymore. It's going to go down and down and down all the way to negative infinity. So as x goes to negative infinity, my graph goes down to negative infinity. Same thing over here. If we start at the origin and go to the right, as x gets positive, it's going to be going up forever. So as x goes to positive infinity, my graph is going up to infinity. Okay? If the degree is odd and my leading coefficient is negative, this time, same thing, but this time, as x goes to negative infinity, this time my graph is going to positive infinity. So as x gets very, very small, my graph is getting very, very big. Okay, it's going up forever. On the other hand, as I go to the right, as x goes to positive infinity, as x goes to the right forever, my graph is going to be going down to negative infinity. Alright, this time, if the degree is even for both of these, but the leading coefficient is positive, you're going to have what looks somewhat like a W shape. It's going to be ending and starting going to the same direction. The same thing over here. If the degree is even, it's going to be ending and finishing, beginning and finishing going in the same area. So as we go to the left forever, as x goes to negative infinity, my graph is going to be going to positive infinity if my leading coefficient is positive. If we go to the right, as x goes to positive infinity, my graph is still going to positive infinity. Down here, just backwards, as x goes to negative infinity, my graph is also going to negative infinity. As x gets larger, as it goes to positive infinity, my graph is still going to negative infinity. Okay, so what we're going to look at is example 4 here. And mine's already got the answer down here, so I'm going to cover it up here. It says, what is true about the degree and the leading coefficient of the one where the graph is shown here? So what we have to look is at the ending and beginning behavior. And as we go to the left, as x gets smaller and smaller, my graph is going to negative infinity. And as we move to the right, x is going to positive infinity, which means that the graph is still going to negative infinity. And what we have nice here, we still got our table up here what we can look at. And this one looks most closely related to this one, where my degree is even and my leading coefficient is negative, which means that, to me, option D looks to be what the answer should be. And it is. Okay, we'll move the book out of the way here and do the last couple examples, which shouldn't be too bad. But actually, the last two examples are graphing, so I'm going to get my graph paper out. And a lot of this will be done on the calculator, so hopefully you have a calculator handy. Let me zoom back out here. Alright, example 5 is the last example. And I know this video is getting a little long, but a lot of stuff to cover. Example 5, it says graph the polynomial. And there is no set way of doing this. It's just using your calculator, your table of values, and plotting points. Okay, so we can look at this real quick. It's in standard form. My degree is 3, which is odd. My leading coefficient is -1, which is negative. So if we look at our table that we just did, where you have an odd degree and a negative leading coefficient, our graph should look something like this. It may not be exactly, but it's going to be coming from the left way up top and going down forever. Okay, so let's see if it has that same behavior. It may not look the same, but it may have the same behavior. So let's draw ourselves a big graph here. Hopefully we'll have enough space here to do it. And just pull your calculator out. Go to your y equals. And make sure all these plots aren't highlighted. I don't know why mine are. And just type in the original question. Negative x to the third plus x squared plus 3x minus 3. And just graph it. And again, my calculator's way off here, so I want to have to hit zoom 6. That way I have the standard graph here. And look at it. It looks very similar to what we should have. Okay, it's going up forever, it's going down forever on left and right. So we just need to figure out what these points are. So hit second and graph to get your table of values and just plot some points. Okay, I'm going to start with -3, but I really don't want to start with -3 because that's a high number. I don't have any room in my graph to do that. So I'm going to do -2 and 3. So left 2, up 3. -1, -4 is the next one I'm going to do. So -1, -4, 1, 2, 3, 4. 0, -3 is the next one. So 0, -3 is right here. 1, 0 is the next point, right here. And the last one I'm going to use is 2, -1. And I'm just going to follow the pattern, go back to my graph here, of what it looks like. Okay? And I know that -3 is going to be 24, so it needs to be coming up from way up here. It's going down, it's going back up, and it's going back down. Okay, doesn't have to be a perfect graph, but it should look very similar to this. Okay. All right, and then question B, same thing, just a different example. It says take f of x, which is x to the fourth minus x to the third minus 4x squared plus 4. And so let's first off see the degree is 4, which is even. And the leading coefficient is 1, which is positive. So if you look back to your chart on the previous page, you will see that degree that's even and has a positive leading coefficient will look something like this. That's kind of what the graph on the previous page shows you, where it is starting and ending going to positive infinity. So let's go to our calculator. Let me drop my graph first so we have it ready. Go to my calculator, go to y equals, clear out what I have, and then type in the new one. X to the fourth minus x to the third minus 4x squared plus 4. And again, graph it just to make sure we're in good shape here, but look what happens. It's not exactly the same. You can tell that the curve is way up here and way down here, which isn't, always the same, but it's starting and finishing going to positive infinity. So go to your table of values, second and graph, and just plot these points. We're obviously not going to use this one. I don't want to go all the way to 76. I'm going to start at -1, 2. I may need the other one, we'll see. 0, 4, which is right here. 1, 0 right here. 2, -4. And then 3, 22, which we know is going to be way up here. So what's weird about this one here, if you were just to plot these points and not know what the starting and ending behavior was, it would almost look like just an N shape. But we know that -3 is 78, which is way up here somewhere. And then we know also that the next point to the right is 322, which is also way up here. So you just have to kind of use your little bit of imagination here, but it's going up, back down, and then back up again. Again, doesn't have to be perfect, but I just want to see that you know what the starting and ending behavior is.